Did you know there's 5 times more dark matter than there is normal matter? So the atoms that make up the tables, so the chairs, us, the stars, and the galaxies, is only 1/5 of all the mass that's out there. So with all that extra mass means a lot more gravity. With more gravity, that's going to affect the motion of the stars around our Milky Way. It's going to bend light so that the light from a distant galaxy is distorted as it comes through the dark matter to us here on Earth, and astronomers can see that. So therefore, we really understand, we know that dark matter is there. The problem is we don't know anything about its nature. We don't know its size, we don't know its composition. How does it interact with other forces other than gravity? Our experiment is called CDMS. That stands for Cryogenic Dark Matter Search. So we build detectors of germanium and silicon, and we make them very, very cold, only a few milledegrees above absolute zero, so that every single atom is very still. And then, when a dark matter particle comes through, it can bump one nucleus out of place, and these detectors can sense that one displacement of one nucleus, and then it will tell us, yes, a dark matter particle has gone through. We've had many phases of the CDMS experiment, and every time we have more sensitive detectors, we also see background signals that we're now sensitive to and were not before. That means that every time we build a more sensitive detector, we need to decrease the backgrounds. So another name for radiation is just a fast-moving particle from a decay. And because our detectors are built to be sensitive to fast-moving dark matter particles, they're also sensitive to any kind of radiation, either natural radioactivity from the rocks or cosmic rays that are always bombarding the Earth. To get away from the cosmic rays, to shield from them, we go deep underground. Every time we've built a more sensitive detector, we've had to go deeper. So we started with an experiment in the 1990s on the surface. Then we went to the Sudan experiment, which was in a mine in northern Minnesota. And we are now building SuperCDMS at SNOLAB, a laboratory in Canada, which is 2 kilometers deep underground. When we put a detector 2 kilometers underground, we have all of this Earth, and we call it an overburden, which filters out the cosmic rays. The dark matter interacts very weakly, so it manages to come down to our detectors. On the other hand, when you get underground, you have rock around you, and that rock has natural radioactivity as well. So coming underground was fine for getting rid of the cosmic rays, but how do we get rid of all those fast-moving particles that are coming from the natural decay in the rocks around us? For that, we need to shield the detector, which is where LEMUR-PAX comes in. LEMUR-PAX is an expert at shielding human beings from dangerous radiation. The same technology that protects human beings from dangerous radiation can be used to protect our detectors from natural, normal radiation that isn't so dangerous. Eventually, we want our detectors to see approximately 1 neutron sneaking into that shield every 2 years. The shield has to protect the detectors not only from the natural radiation on the outside, but the shield itself must not produce additional radiation. If the shield itself, being made of materials from the Earth, will have some natural radiation, then putting a shield in the way does no good. We don't want to create additional radiation from the shield. We went with LEMUR-PAX because LEMUR-PAX is able to cast lead bricks that are free of much of this natural radiation. So in order to protect our detectors from the natural radiation, you need a combination of lead and plastic. The plastic helps to shield from neutrons and the lead from the gamma rays. So this makes a complicated envelope of different materials, and all of which must be assembled in such a way as there are no cracks through it. The shield is also quite large. It's 4 meters high and 4 meters in diameter. and it weighs more than 100 tons because of all the lead. So this complicated shield needs to be assembled ahead of time right here in the Lemmerpax factory in order to see that it all fits together and to produce an assembly drawing and an instruction sheet, because it will then have to be disassembled and shipped to Canada and then brought down underground 2 kilometers deep to be reassembled. This shield is quite complicated. It has many small pieces that all have to fit together. Therefore, it is entirely being assembled at the factory first in order to produce also an assembly set of diagrams in order to be able to reassemble it at its new location. It will be disassembled at the factory and shipped to Canada, at which point all the pieces have to go underground in a small lift and then reassembled underground 2 kilometers below the surface of the ground. Because even the dust that is in a room can have trace amounts of radioactivity. It's very important to keep every piece of this shield clean. It has to be assembled in a clean room. It has to be packaged in such a way as when it is shipped, it is maintained in a clean way. It must be brought underground, 2 kilometers underground into a mine that is actually a 2000 class clean room itself. Once we've designed a shield, we still need to find the parts of the shield that will be very low background. So we went to Lemmerpax because they did a very good job with the lead, but we discovered at the same time that they had much experience in producing shielding for high radioactive areas, which is the same technology we need for the low background. So our simulation provides us with an idea of what material we need and how thick it is. But in order to realize that as an actual shield, we needed to go to Lemmerpax and ask them what would be the engineering design that would actualize what we had done with our simulation. So in fact, the very first experiment which we built underground in northern Minnesota had some very low background lead, which everyone called Nantes lead. By researching what is this Nantes lead that we had that was very low background, we discovered that in fact it was the same lead that was also here at Lemmerpax. So I researched this Nantes lead and discovered it came from the same lot of ingots that still existed at Lemmerpax, which meant that we could get that same quality lead by having a shield built by Lemmerpax. As you can imagine, a complicated engineering process requires a lot of communication. We met by teleconference every couple weeks with the Lemmerpax engineers to understand how progress was going on the design, and after that, during the fabrication phase, we have had weekly updates and photographic summaries, as well, in fact, as a particle counter, which is in the clean room, whose data we monitor. About a year from now, the shield will be assembled, and we will begin to turn on the experiment, and maybe we'll find dark matter in the next year. I hope so.